Okay, then perfect. Before I get in, really quick, I'm Kevin Stumpf, the co-founder CTO of Tecton. We're a data platform for machine learning. And before starting Tecton, my co-founders and I, we were all over at Uber, where we built Michelangelo, which is a centralized machine learning platform that enabled pretty much all of the ML use cases over there. And I'm going to talk a little bit about that, what exactly we did over there at Uber, how it informed what we're building here at Tecton. I'm also going to talk about what is a feature store and how does it enable operational ML and what even is operational ML in the first place. I'm going to talk about various different fairly technical topics, but also high-level topics around how operational ML and ML in general enables a bunch of different business use cases. Now, feel free to jump in anytime with any questions that you have. So it's not just going to be a complete monologue over the next 30 minutes. Perfect. With that, let's dive in and see what is operational ML all about. To best understand that, we want to take a look at the comparison between analytical systems as well as operational systems. On the analytical system side, you've got typically decisions that are made by a human who has to be in the loop and who may use a machine learning model in order to inform their decisions. That could be ML models that predict sales forecasts for the future, and then print out those sales forecasts on a report that is sent out by email or that feeds into some dashboard that some executives in your company are going to look at. Or maybe things like churn prediction models that run maybe once a week or so and predict what are the customers who are most likely to go to churn out of your customer base. So you may want to send them a promo code so they're going to stick around a little longer. Now, those analytical machine learning approaches, they're all about generating offline insights. And it's typically using data that is available in like a data warehouse, like a Snowflake or a Redshift cluster, or a data lake like S3 or an HDFS cluster. And if we compare this to operational systems, we see that operational systems, and in particular operational machine learning, really drives mission critical use cases that affect your customer directly in production. This could be things like fraud detection systems or real-time pricing, product recommendations. So really anything where the system has to make a decision in the moment while your customer is interacting with your system. And so it's mission critical. SLAs are really, really important. The system needs to behave very well and reliably at high scale. It needs to be able to make predictions at very low latency of 100 milliseconds or less typically. And these systems plug not just into your data warehouse and your data lake, but they typically also have access to your streaming data systems like your Kafka cluster or data sources that I talk a little bit more about later. And at Uber, we built a lot of experience with operational machine learning. So let's take a look at how we did this. At Uber, we built this Michelangelo platform that I mentioned earlier, and it powers a ton of different operational ML use cases. Also, fraud prediction, recommendations, dynamic pricing. It even helped power the self-driving cars that we had, safety prediction models, all kinds of different fairly fascinating ML use cases, which was of course possible because Uber was at that time the fastest private growing company of all times. Obviously an online business, so it was collecting tons and tons and tons of data that you could leverage for all kinds of different interesting ML use cases. And in the very beginning, before Michelangelo was built, it was quite hard to train an ML model and get it all the way into production. And on the next slide, I'm gonna explain why that is. But it took us typically 6 months, a year to get an ML model all the way into production. And in order to get this time down from 6 months to an hour, maybe a couple of days at best, we had to build this standardized and centralized platform which could automate a lot of the workflows that are necessary that you have to go through in order to get your ML model into production. And so as a result of having built the system, we eventually had hundreds of people use it, and the platform powers thousands of models in production, all these various different use cases that I mentioned above. So let's take a quick look at why is it actually so hard to get an operational ML model into production? Why does it take 6 months, 12 months? The reason for that is that you first have to recognize that a machine learning application really consists of three different parts: the application itself, the model, and the data. So let's make this a little bit more concrete. Let's say you've got an Uber Eats or a DoorDash mobile app, which makes restaurant recommendations. So you would typically have a microservice, some API hanging out in your backend, which is able to make these recommendations for any given user. And that is your application. Now, that microservice needs to talk to a model, which, given a given user ID, is able to make a prediction about what are some restaurants, what are some cuisines that this user may be most likely to want to book from right now. And then the third part is features, the data that the model is actually using in order to make the prediction and provide the recommendations. And that could be things like, what's the cuisine that this user has most frequently ordered from last month? What is the set of restaurants this user has clicked on in the last 30 minutes or 10 minutes? And so it's a lot of different data, a lot of different information that would feed into the ML model in order to eventually make the prediction. And so now you can imagine these three artifacts, application, models, and data, is required in order to build and run a model in production. When it comes to the applications, like those microservices, we've gotten pretty good at developing them and deploying them so we run them in production. I'm sure you've heard of CI and CD pipelines, which are these DevOps pipelines, which make it very easy to, where you make a little change to your microservices code base, check it into a GitHub repository, and then you've got like a Jenkins or whatever it is, DevOps pipeline running, which tests your code, builds it, and then eventually pushes it into production to some, say, Kubernetes cluster, where now a Docker container is going to run the latest change that you've pushed. For models, it's a little bit harder, but it has become possible over the last couple of years to ease the pain of developing, training a model, and pushing it into production. For that, we now have MLOps pipeline systems and MLOps systems like SageMaker or Kubeflow that help you train a model in like a Jupyter-like notebook environment, and then package it up and put it behind an API endpoint, like a REST interface or something like that. What we so far haven't really figured out is, how do we develop features, the data that you need in order to train an ML model and make predictions? And how do we productionize those features? Typically, the way that works today is that you have a data scientist do some data wrangling in a Jupyter notebook using Python code, using all kinds of different libraries, by importing some raw data from various different data sources. Then you do the data wrangling. Then you've got a data frame with all the different columns, all the different features that you're happy with, that you want to now train your model on. Now you've got your model, you backtest it, you're happy with it, and now you want to put this whole thing into production. But the question is, how do you get these feature transformations into the production system? The way that is typically done is that you have the data scientist hand the Python code over to a, say, Java developer, some ML engineer who understands production systems very well, who then goes ahead and re-implements the transformation code using production-ready code and goes through the whole pain of productionizing it to make the data eventually available in the system, so you can have your model in production and have the model be able to actually find and receive features so you can make a prediction. And I'll talk a little bit more about that in a second. And to us, we've really observed at Uber and outside with Tecton that solving this data problem and solving these data problems around machine learning is really the missing key to making the development and the productionization of operational ML systems much, much easier. And as a result of that, we built this data platform for ML, which we call the feature store. We first coined this name over at Uber when we built Michelangelo, and now it's become a whole category in the ML stack. So let's take a feature store is really the interface between your organization's raw data sources as well as your model training systems. And so it's this intermediary interface, this intermediary layer and then serves the features to both the training system and your model serving system. Your data scientist is the primary user of it, who using the feature tool defines new features, deploys them to production, and then shares them. So let's now take a quick look at what are actually the hard technical problems under the hood that a feature store solves. First, and actually the hardest problem of all of them, is that extracting and serving features is really hard for a variety of different reasons. One, the raw data sources can be all kinds of different data sources. It could be batch data sources or streaming data sources or real-time data sources. And it turns out that they have very different characteristics about how much data do they have available, how fresh is the data in there, and what are the types of aggregations and transformations that you can even run on them. So you can take a look at like a data lake or a data warehouse. Those systems are known to typically contain the entire history of your organization's data, but the freshness is oftentimes fairly low. Maybe data gets landed in there every couple of hours or every couple of days. Your transactional systems, like your MySQL or Postgres database, contains typically all the transactional data. So the very recent history, but the data freshness may not be, like it's fresh, but it's not the freshest it could possibly be. For that, you've got prediction request data. And let me motivate this with an example too. Prediction request data would be if you have an e-commerce website and you want to, again, recommend items to a user's search. Now, the user is going to search for in the text box for some item, like red shoes or whatever it is. And this string that was just inputted into the text box, that is now prediction request data, which you have available right in the moment in which you want to make a prediction, because you want to take a look at the red shoes that was just that the user has been searching for, and you want to combine that information with additional information that you know about the user, like what type of stuff has the user purchased in the past. And now a challenge is that these different systems support different types of transformations. You can imagine that a data warehouse supports all kinds of large-scale batch aggregations, like really large joins, like group bys and whatnot, where you look at the whole history of an organization, and that would allow you to develop transformations like what's the lifetime transaction count of a given user? How many times has somebody ordered in their whole life a Thai dish at a DoorDash or Uber Eats app? Streaming systems like Kafka and whatnot, they wouldn't allow you to do this very easily, because typically the amount of data that you have available here is very limited. It could be just the last 1 week, the last 2 weeks worth of data, and that's not enough to calculate the number of the number of times that a user has in total ordered a Thai dish at your restaurant. But what these streaming systems are really good at is to run time window aggregations, which could be what is the rolling click count of a user over the last 7 days on a given restaurant, like a Thai restaurant. You can run these types of aggregations and feature transformations very easily, or much more easily at least, with a streaming system like Kafka. And then prediction request data, again, this is the data that is passed into the system as you're making a prediction, like the search query string. That only allows you to do row level transformations, where you can take this one row that is passed in apart, retransform it and whatnot, but you cannot run larger aggregations, of course, on top of it. Moving on. Now, the next problem is, what happens if you actually want to now use, say, an aggregated feature in production to make a prediction? Imagine, again, it's the lifetime number of Thai dishes a user has ever ordered. You could imagine that you've got this Uber Eats backend, which wants to know this information in order to make a prediction. Now, the most naive implementation will be that your backend goes straight to your Snowflake or Redshift cluster and runs this query and asks, okay, what's the total lifetime number of orders of this user? And you can imagine that this query is likely going to take minutes, if not longer, in order to produce this fully aggregated value. And as a result of that, your model would likely time out and the user would never get the recommendation. So it's obvious that you cannot have your production system just go straight to your data warehouse to run these really expensive compute jobs. So what options do you have? You will have to decouple the feature calculation from the feature consumption and have this intermediate store, like basically a caching layer in between. So you'd have, say, a batch job that runs once a day, once an hour, whatever the right frequency is, to pre-compute the lifetime number of purchases for any given user, and then store that data in your production store, where your model can now pick it up from and make the prediction. Now, this production store should ideally be one like a key value store, say Redis or DynamoDB or Cassandra, one of these systems that is built for high scale and that has very low read latency. But of course, now you have a problem, which is that this feature is getting stale the moment that it has been pre-computed and put into the production store. So you now have to figure out what is the optimal trade-off between the freshness of your feature and the amount of money it costs to calculate and store the feature in the first place. And it really depends on the use case. It really depends on the feature of what the optimal trade-off is. Most companies, most users don't pay too much attention to the costs. They often have a pretty good idea about what's the optimal freshness, but even that is fairly frequently ignored. And typically a rule of thumb is that the longer the aggregation horizon is, the less frequently you have to pre-compute your value. Because if it's like a lifetime aggregation for a user, the variance in that feature value is not going to change from second to second, most likely. It's going to change maybe from day to day, maybe even from week to week. But if you have something like a 10-minute click count to predict ads on a website, you really want to update such a feature value every millisecond or right before you make a prediction, ideally, because the variance over a shorter time window is much higher. And now you can imagine that all of this gets really hard and really fun when you combine raw data from all kinds of different data sources, from a batch source, from a streaming source. And then for the fun of it, you also throw some real-time prediction request data in there, like the search string that I mentioned, where somebody punches in red shoes. Building such a data pipeline architecture is extremely hard to get right. And that's why you see these operational ML projects typically take multiple months, if not longer than that. And then once they're built, once they're working, then nobody wants to touch the system anymore because it was so hard to get it up and running in the first place. And then you have all kinds of downstream problems that I'm going to get into a little bit later. Another fairly common trap is was referred to as train serve skew. And that happens when you train your data, when you train your model on data that is different than the data that you feed to the model at prediction time. And that could happen, for instance, if you've got logic discrepancies where the implementation of your code that produces the training feature set is different from the code that produces the serving feature set. And that can very easily happen in this example that I gave earlier, where you've got your data scientist who builds features in a Jupyter notebook and then trains their model. And maybe they've got some Python code or whatever it is, or some SQL code that generates offline these training features. And then that user hands over this code to the ML engineer, the data engineer who builds the production-ready pipeline and re-implements the code. Now, it's very easy that both of them actually use different code to calculate these feature values. Maybe the data scientist treats a null value as a 0, while the production engineer actually imputates the null value with the average feature value for all other users. And the more of these discrepancies you introduce, the worse your model is going to perform. And it could even be the case that you just have one discrepancy and you train a model, you look at it, you back test it, it looks great, but then you throw it into production, nothing's going to work. And now you have to go on an arduous debugging journey to figure out what's actually different. Why is this model not performing the way I'd expect it to perform? And there's no easy logs or anything like that that you can look at to debug this type of problem. So the right way to solve this problem is to actually use the exact same implementation to calculate the feature values offline as well as online for serving, because that simply makes the introduction of these logic discrepancies pretty much impossible. Another common source for train serve skew is introduced by timing discrepancies. Let's take a look at another example here, which is, again, the DoorDash food ordering service, where you want to predict how long is it likely going to take for a restaurant to finish an order. And a very important signal to make this prediction is the trailing 30-minute order count. Like, how many orders have come in to a restaurant over the last 30 minutes? Why is that a good proxy or a good feature? It's a good feature because it's a proxy for the busyness of the restaurant. And the busier the restaurant, the longer you're likely to have to wait until your order is properly prepared. Now, what you would oftentimes do is that at serving time, remember again this decoupling that I talked about a couple slides earlier, you would decouple the feature computation from the feature consumption. And so you may figure out that it's okay to just recalculate this trailing 30-minute order count every 10 minutes or every 5 minutes. Maybe that's good enough, and maybe that's the optimal freshness to cost efficiency trade-off. But now a risk is that if you do this in production, when you train your model, it's much more feasible to actually calculate exact 30-minute order counts. Because you're working in an offline setting, you can run this large batch job, wait for an hour until it has calculated exact 30-minute trailing order counts for any given row of your labeled training data set. And if you compare these two, this is what you would be serving in production. This is what you would be training on. Now your model that you're training is getting used to seeing 100% accurate trailing 30-minute order counts. And it's not being trained on the fact that in production, it will see much noisier data where you have these step function changes in the trailing order counts. And you can expect that the model is now going to perform worse than if you had just trained it on the same distribution. And now, finally, another good source of train serve skew is introduced via what's called data leakage. And that happens if at training time for a given row of your labeled data set, you introduce information which at that point in time was actually not available. And let me make this again more concrete. Let's say you have an Uber or a Google Maps model which wants to predict how long is it going to take to drive from Berlin, Germany down to Munich. Now you can take a look, your training data set could contain a bunch of like thousands of historical trips that people took from Berlin down to Munich and how long they each took. And now you could have a feature in there as a data scientist, which indicates, was there an accident on the road, on the highway, or the number of accidents on the highway. And you can expect that as you train this model, it's going to become more and more predictive and more accurate the more information you introduce about the accident that happened on that very same trip. Now, of course, if you throw this model into production, the model is going to perform awfully, because when the trip starts, your model and the system has no idea whether an accident is going to happen later on the road. So what you have to ensure is when you train this ML model that you only look at data which has been known at that point in time about anything that had happened in the past, but nothing in the future. And so you could look at what's generally the historical traffic jam and accident distribution on this highway which connects Berlin and Munich. And if you don't do this, again, like all these train serve skew sources are really horrendously hard to debug and figure out. And so it's best to just ideally have a system which prevents you from ever introducing these types of really nifty issues into your system. And you may have guessed it, a feature store or a data platform for machine learning solves these problems that I mentioned for you. It extracts and serves these features from all of your data by avoiding all these problems that I just mentioned. It hooks into your batch data sources, your streaming data sources. It can even mix both of them, pre-computes the feature values, serves those feature values to your ML model in real time at the latency that you need. And it serves the historical features without introducing train serve skew to your training system. So you can be in your Jupyter notebook, wherever it is, and go to the feature store and ask for the historical feature values so you can train ML models without running the risk of introducing train serve skew. And the feature store also allows you to actually tune this trade-off that I mentioned earlier of the decoupling of feature calculation and feature consumption, where you can play around with different variables and see, what do I actually need? What freshness do I need in order for my model to still perform well? And you want to basically reduce the freshness to the lowest possible, where you don't see any detrimental behavior on your model performance anymore. All right, that was problem one. The other problems are a little faster to go through. But the second one is that your ML teams are stuck building these complex data pipelines that I showed about earlier, where you've got the stream, batch sources, or real-time data sources that you need to run these transformations on top of to pre-compute these features. All these complicated data pipelines are built by the ML teams. And now the data scientist is not empowered anymore. The data scientist now has to work with the data engineer or an ML engineer, beg them to make this new feature pipeline a priority. The data engineer will put in their backlog, eventually get to it. And by the time the pipeline is built, maybe the data scientist already left the team. Maybe they completely forgot about their idea. And you lose a lot of, a lot of value and a lot of valuable time here. Because as I'm sure you guys know, data science and machine learning is really more of a science where oftentimes, in contrast to software engineering, you don't know ahead of time what is going to work. You have some ideas, you have some intuitions around what would you as a human use to predict a certain outcome. And so you try it out, you implement this little feature, train a model, you backtest it, you're happy with it, and now you just want to throw it out into production to see, is that actually going to work? Was I right? Was my hunch here correct? And you really want to shorten down this iteration loop as much as you possibly can, because the faster you can iterate on new ideas, the more your data scientists are, of course, empowered, the more experiments they can run, and the faster you'll get to a model that is actually worthwhile in production. With a feature store, data scientists are unblocked. They can create production-ready features directly themselves, try them out, backtest them offline, commit them to the feature store, and then the feature store makes these feature values available in production immediately. Third problem is that without a centralized system, you don't have standardization of these data pipelines, and you'll find a lot of duplication where the different data engineers in your organization, where very frequently actually you find organizations where you have more than one data engineer mapped to one data scientist. So you may have 3 data engineers for every single data scientist in an organization. So all these different data engineers, they implement data pipelines, feature pipelines. They may very well not quite know what the other data engineers are working on. They may re-implement the exact same data pipeline. And as you know, a data pipeline is actually can be an extremely expensive component to run, depending on the frequency you run it with and the amount of data that is crunching. It could cost real money and really impact the bottom line of your business. And so if data engineers don't know what the other data engineer is doing, they don't know what else they could be leveraging and reusing, this could have material cost implications on your business. And a feature store manages these features as data assets, which are built in a way where it's very easy to share them with other teams, where it's very easy to even discover what are the features I already have available in my company. What have other people been building over the last couple of months, years? What are features that are really highly trusted? What are some features that are currently running in production? Let me just try those out so you don't have to create and introduce a new feature, which could cost a lot of money. And then finally, let's look at how these models that are running in production, once you've got them out there and you're happy with the results, how they break. Typically, it's not that the model itself breaks. Like, we've gotten pretty good at hosting a model container behind a microservice, which runs in your Kubernetes cluster, whatever it is, and it'll run fairly reliably. But at some point, you'll notice that your model makes pretty poor predictions. Common reasons for that is actually that the data is breaking rather than the model itself. The reason for that may be that some upstream data source, like your Kafka stream or your data lake or your table in a data warehouse, suddenly is not receiving any data anymore. And now, given that you have this data outage at the upstream, you're not going to have feature values anymore that you can rely on. So your predictions are going to go off the deep end. Similarly, you may find feature drifts where maybe the world is just changing. Maybe you don't have an outage in your data system, but maybe the behavior of your users is changing. And so feature drift means that, say, if you look at a numerical feature value, you may notice that suddenly the mean or the standard deviation starts to shift because, again, the user behavior has changed. And imagine that you are building an ML model that predicts hashtags or tweets on Twitter. Now, if suddenly some hot news happens and suddenly a specific topic starts trending, this will very likely change users' behavior. And as a result of that, you actually now need to retrain your model because all the feature distributions have changed. And when that happens frequently and often, then you want to build actually these online learning systems which retrain the model automatically in production. And Twitter has built some pretty sophisticated systems there. And now, another really fun one is that you may have opaque feature subpopulation outages. Now, what do I mean with this? Quite of a mouthful of a statement. Again, imagine that you have this DoorDash recommendation system, and you monitor the performance of this model. And you monitor it on a global level. So you see this whole world, DoorDash or Uber Eats is doing really, really well. But it turns out that you actually have an outage in Italy. Suddenly, all the feature calculations in Italy are broken. And as a result of that, the restaurant recommendations in Italy have gone up the deep end. Now, on a global scale, the number of orders isn't that many from Italy that the global metrics would tank and that somebody would start looking into it. And so as a result of that, you would actually have to have a system which is able to look at the different subpopulations of your features and see, are my feature distributions in Italy looking healthy? And are they looking healthy in Germany and France and whatnot? And be alerted in case some subpopulation starts breaking. And then finally, a very fun one is that oftentimes, even when you do know that you have a data quality issue, some data pipeline is broken, it's often not clear who should own it. Who's the primary owner of a data pipeline, of a feature? Who are you going to go to? Maybe the data engineer who first built it has left the company. And there is still, even outside of just feature stores, even outside of machine learning, there's still, we're still figuring out the best practices organizationally to identify and figure out who should own data issues and who should fix them. Feature stores monitor your data flows, as you may have guessed, and they're very well positioned to do this because they drive the feature pipelines. They do calculate these features. They do serve those features, so they can look at what do the feature distributions look like when you train a model? What do they look like now in production? Does that look the same? If it doesn't look the same, you probably want to alert the user and let them figure out what they want to do, whether they want to retrain the model or whether they have an upstream data outage. All right, this is a subset of all the problems that, or the most important subset of problems that a feature store solves. And bringing it all together, this diagram here shows you the main components of the feature store. So how does it solve all these problems if you look at really the internals of this feature store? Primarily, it has a registry where you register all the different features with the feature transformations that you have. It has a storage system. It can run transformations. It can serve feature values, and it monitors these feature values. Now, and a really, really important thing to call out here is that a feature store is actually not a black box system that you bring into your data stack, which implements its own transformation engine and tries to compete with Spark or with Flink, or tries to implement its own key value store or its own offline store to store feature values. That's not what it is. A feature store takes advantage of your existing data stack, your existing data infrastructure. And so if in your data infrastructure, you typically use Spark for production pipelines, then a feature store, at least Tecton's feature store, is able to plug into your Spark cluster and run transformations in your Spark cluster. It also stores feature values in your offline store, whether it's a data lake on S3, Delta Lake, Snowflake, Redshift. It just plugs into the existing data stack that you have and gives you basically this machine learning ready layer on top of it that allows you to very efficiently and without introducing all these common mistakes, train and deploy ML models. And now let me show you really quick what this looks like, how you actually use a feature store in the ML lifecycle. Let's look at how you define a feature with Tecton, how you generate training data, and how you fetch features for real-time predictions. So let's zoom into these different code snippets. With Tecton, we believe that features should be defined in a declarative way in a file system, in files which you can back up in a version control system like Git. So you'd find with Tecton feature definitions like this laid out in Python files in a directory, which you would typically back up again in Git or whichever version control system you have. And here you define, okay, what's my feature transformation, like a SQL query. It could also be PySpark code or Python code. And then you annotate it with some metadata around, of course, the name of it. You indicate whether you want to make the data available offline and online. And you indicate which data sources it depends on and what entities, like is it like a user or a transaction or whatever it is, that this feature is associated with. When you train your model, you would use Tecton's Python SDK, which you can load into any Jupyter notebook or any other Python environment in your laptop, whatever it is. And you ask Tecton to fetch historical feature values for you so that you can fit your model and train your model against it. And then finally, you can use Tecton's gRPC or API interface or REST API interface or the Tecton SDK to fetch feature values from the real-time system at very low latency. And of course, it supports high scale to make your predictions in production. To tie it now all together, how does a feature store help a data science and an ML team? It allows them to build more accurate models by leveraging all of the data sources and by ensuring data consistency between training and serving. It also allows you to get models into production much, much faster within hours instead of weeks. And something that I'm personally very passionate about is it brings DevOps-like best practices to feature development and really to machine learning development altogether. All this stuff that we figured out in the last 10, 20 years even to some extent about how to make software engineering more efficient and for typically like SaaS software businesses, we're bringing these DevOps-like practices to feature development and to ML development as a whole by managing features as code in these Git repositories and making it very easy to integrate those feature repositories with your existing CI and CD pipelines that you use to drive your software development. And then really quick case study, Atlassian was our first customer. We replaced their internal feature store and allowed them to deploy models within days instead of months. Now they don't have to put any engineering resources to it anymore, and their model accuracy went up by 20%. If you're curious about feature stores, you want to learn more, there are two options that I'd recommend you could look at. If you really care about open source, you want to have something that's free, something that you can manage on your own, something that you can even customize on your own, that's lightweight, you can go to Feast. It's an open source feature store that we're massively contributing to. And if you care more about a fully managed cloud service that supports transformations as well, that comes with SLAs, you could get a free trial from us at Tecton.ai. And that would be it.